Okay, good afternoon, everybody. Welcome to our first colloquium of the year. I'm very pleased to introduce Alice de Villers from the University of Western Australia. Alison comes from Belgium. She received her PhD from the Université Libre de Bruxelles in 2002 with a grant from the Fonds National de la Recherche Scientifique. After a couple of postdocs, she has been a senior lecturer at UWA since 2011. She's also an active member of the Center for the Mathematics of Symmetry and Computation. Her talk today is entitled Combinatorial Designs in Symmetry. Before I hand it over to Alice, I just want to remind everybody that we will be recording this talk. We'll open up for questions at the end, at which point, please feel free to unmute yourself. With that, thank you again, Alice, for being here. It's all yours.
Thanks, Justin. So I'm going to talk about combinatorial designs and symmetry. I'm part of the Center for the Mathematics of Symmetry and Computation, which was founded by Cheryl Prager some years ago now. And before I get into what combinatorial designs are, which is the main topic of this talk, I just want to talk a bit about what do we mean by symmetry? So we're like a bit of a conceptual question. What is symmetry? First thing I did, I looked in the dictionary and it said balanced, something that has balanced proportion is something that has symmetry. Probably if you asked somebody on the street, that person would say something like that, like a face has symmetry, something like that. If they remember maybe from school, they might remember Euclidean symmetries. So things like translations, rotations, reflections, things like that. That's closer to what I mean by symmetry. So if I try to like conceptualize what does that mean? Well, so a symmetry is going to be a permutations of the points. So in this case, the points in the plane. So permutation means like a bijective map from the plane to the plane, which preserves the notion of distance. And if you just ask that, you get these translations, rotations, reflections. So you want that if 2 points are a distance, I don't know, 3 centimeters, after you've done you mixed your points around, these 2 points are still at the distance 3 centimeters, and this has to be for all pairs of points. So it's a permutation of the points which preserves distance. So now I want to generalize this concept to not just the Euclidean plane, but some other things. And so in the very general setting, if I have an object, so here I'm not thinking now an object in Euclidean space or anything, just I'll give examples in the next few slides what I mean. So just an object could be a graph, a vector space, the Euclidean plane, or anything, or in my case, it will be designs. But so a symmetry of an object is permutations of the elements that are in the ground set of this object, and that we want this permutation to preserve whatever the structure of the object is. So that's what I mean by a symmetry. I'm always talking about the symmetry of something, of some kind of structure. Once you have symmetries, you can compose them and you can inverse them. You have the identity symmetry, which is when you don't move anything. So it's also a symmetry if you do a permutation that doesn't change anything. It's also considered a symmetry. And all of these together satisfies the axioms of what's called a group. That's called the group of automorphisms of the object. Symmetry is just an easy word, but the more mathematical word is we use the word automorphism. So auto is like self, and morphism is shape. So self shape, something that keeps the shape. So automorphism is just the same as symmetry. So they form a group. If you know what a group is, if you don't, doesn't matter. It's just something where you can compose things together and inverse, and I have an identity. So some examples. Well, the easiest example, if you just have a set, and then there is no structure, it's just a set, then any permutation is a symmetry. Any permutation of your set, so bijective map from omega to omega, and the automorphism group is called the symmetry group, and is just denoted sim omega, like here. Very often we use omega for like an object or a set or something like that. And if I can do just a quick plug, I have some colleagues that have a mathematical blog, and it's called Sim Omega. Another example, it's a little bit with a bit more structure, would be, for instance, a vector space. Then what would be a symmetry of a vector space? Well, it would be a permutation of all the vectors, which preserve, well, what gives the structure to the vector space is the fact that you can add vectors and the scalar multiplication. So it's a permutation that preserves that. So in other words, it's a bijective linear map, and all these symmetries together forms what's called the general linear group. So that's another example. More of a discrete example, graphs. A symmetry, then what the structure is, a graph is just like a set of nodes and then some edges in between some pairs of the nodes. So a symmetry in this case is just a permutation of, so the nodes are called vertices, which preserves all the edges. So for instance, you can easily see that if I do a fifth of a turn like this, that's a symmetry. Okay, it preserves, it maps an edge to an edge. But there are way more symmetries than this. My symmetries don't need to be induced by some Euclidean symmetry. Is just a map, is just a permutation of the 10 vertices that preserves the set of edges. That is all it is. So there is actually 120 symmetries for this particular graph. It's called the Peterson graph. So for each graph, there's going to be an automorphism group that is attached to this graph. So a little bit of advertising, Center of Mathematics of Symmetry and Computation. So that's the kind of things we study. We do group theory, which most of the time is permutation group theory, combinatorics and computation. So we study discrete structures, such as graphs, like I showed just before, or finite geometry, finite linear spaces, and also designs, and then the automorphism groups. And then we study, like, if we say we want the automorphism group to have some sort of symmetry property. I'll explain what I mean by that with the design when I talk about the designs. And we try to then like classify or see what we can say about the groups if we impose some conditions on either the group or the structure itself. And here is a list of the current members in our research group. So now I'm going to get into the topic of designs. So designs are a sort of discrete structure, like I mentioned, but a bit different than graphs. It's started with designs of experiments. So it was initiated in the 30s by Ronald Fisher and Frank Yates. and they were looking at questions of designing experiments in agriculture. So very practical field experiments. I'll give an example in the next slide. So this has still lots and lots of applications today in many scientific fields. So the word design comes from to design an experiment. So from the verb to design. So imagine you're an agriculture scientist and you want to do an experiment where you want to compare the yield of different varieties of grain, for instance. So say you have V different varieties, but because there could be an interaction between the environment and the variety of grain, which would alter the yields, you want to have an experiment which is at a few different farms. You don't want to just have one farm where you plant everything. You want to be able to compare in different places. So each farm we'll call a block, and you will have like different farms in different places with different environment conditions. One obvious solution would be to plant in V fields the V varieties at each farm, and that's what's called complete blocks. But that would be very costly to do that. Most of the time, the farms wouldn't want to lose V fields for this experiment. So that's too costly to have this solution. Another solution, you could have V choose 2 farms. So that's how many pairs of elements in V. Take 2 elements from a set of size V, so take all the pairs, or multiple of that, and plant 2 varieties in each farm. That's also very costly because that would require many farms. So a more practical solution is to have a limited number of varieties planted at each farm. So not all the varieties planted at each farm, but more than 2. So that's what we mean by incomplete. That's called incomplete blocks. So not all the varieties planted at each farm. And then for each farm, you'll be able to compare the yield between any 2 varieties planted on that farm. Ideally, you want this to be like a fair experiment. So you want to design the blocks so that the number of times 2 varieties are compared is the same for all pairs. So that's not always possible. Like in practice, it's not always exactly the same, but very similar. But for me here, it's going to be, I want it to be the same. So any 2 varieties are being compared the same number of times. This is the property that's called balance in the design. So if we have designed the blocks that satisfy this is called a balanced incomplete block design. So then once you have set up your experiment that way, then you can use statistical techniques to reach conclusion about the experiment and maybe decide like which variety is the best and should be planted on a larger scale. So this is giving like the motivation how these things were invented. Now, I'm not a statistician, so I can't answer any questions about how you do this last bit. I'm interested in how you set up the block design, and I'm a pure mathematician, and for me, my interest is purely because they're interesting objects in their own right. So here are some examples. Say you have 7 varieties and 7 farms, each with 3 fields that are available, that they agreed to give to the scientists for their experiments, then you could have this solution here. So I have 7 forms here, 1, 2, 3, 4, 5, 6, 7, and 7 varieties, also called 1, 2, 3, 4, 5, 6, 7. And here I say that in farm 1, we plant the varieties 1, 2, and 4. And in farm 2, we plant the varieties 2, 3, and 6, etc. And if you do that, you can check that every pair of varieties is compared exactly once. Like, say, for instance, 3 and 4 are in this one, in the farm number 4. You can have a more visual representation of this. Here in this picture, I have written the varieties as the nodes, and then the farms as colored lines. And I don't really mean a line like in Euclidean line. I just mean the 3 nodes are linked together. Like, for instance, here it looks like a line, but this red thing, circle is the word, I also consider it a line or a block here. So I have 6 blocks that look like straight lines and 1 block that looks like a circle. So block farm number 7, block number 7 has varieties 4, 5, and 6. So it's easier to see on the picture that any 2 points, any 2 nodes are on exactly 1 colored line, colored block. If you've done a bit of projective geometry, you might recognize this as the smallest projective plane, which is sometimes called the Fano plane. So this is an easy example. Now, let's say you have another example. Let's say you have 8 varieties and 14 farms, and each farm has 4 fields available. Then you could do this solution here. So farm 1 has 1, 2, 4, 8. Farm 4 that has 3, 4, 6, 8, etc. So again, you can check that if I take any pair of elements, so let's say like 1 and 2, they are in exactly 3 of the farms. So this one and this one and this one. So it satisfies the property that I want. Here, if I want to have a visual representation, I can write the varieties as the vertices of a cube. And then the farms are the planes that intersect this cube in 4 points. So the faces of the cubes, but also some like diagonal planes like this. So 3, 4, 6, and 8. That's farm number 4. So here, like, I can sort of visualize them in my head, but it would be actually quite difficult to draw all of them and still be able to see anything. So this is another example. For larger V and B, of course, visual representation is not always possible. So you just need to list the varieties for each block, like I did in the tables on the previous slide. There's a couple of ways of doing this. The most convenient is to have a binary matrix, a V times B binary matrix. So the rows represents the varieties, and the columns represents the blocks or the farms, and then you have a 1 if the variety I belongs to block J or otherwise 0. So a binary matrix like this. And if you want to do anything with a computer, that's probably what you would use. It's called the incidence matrix. If you want to write it in a book, then you would probably write more like a K times B matrix with entries coming from V symbols. So 1, 2, 3, 4 up to V, for instance. And then So you have each column represents a block, and in the k rows for that column, you just write the name of the varieties that are planted in that block. So that's a few ways to represent the data, to represent a specific design. So if I want to abstract a bit these concepts, here is the pure math version of this definition. So it's called a balanced incomplete block design, or just a two design. You have a set of points. Instead of calling them varieties, I call them points of size v. So we still use the letter v for the number of points, because it comes from the words variety. A set of blocks of size b, where each block is a subset of points of size k. And then the defining property is we want each pair of distinct points to lie on exactly lambda blocks. So we've got 4 parameters, v, b, k, and lambda. So incomplete means that k is less than v. We want more than 2 varieties per block. So usually we ask also that k is more than 2. And then here it makes things easier when you want to study these things to not allow repeated blocks. But in practice, if this is a real design of an experiment, then you could have repeated blocks. It might sometimes work well to have 2 farms that have the same varieties in 2 different locations. But for me here, I'm going to assume I don't have repeated blocks. That means if I take 2 different farms, they don't have the same, they haven't planted exactly the same varieties. So this is a 2 design. Here, 2 design. And that's because I compare pairs of distinct points. We can generalize this to what's called a T design, or TVK lambda. So it's exactly the same definition as before, but this time I'm asking that each T set of distinct points lie on exactly lambda blocks. So if I take t equals 2, then it's the definition from the previous slide. So this is just a generalization. So the final plane was the 2 design with parameters v7, case 3, and lambda is 1. The cube was a 2, 8, 4, 3 design, but also a 3, 8, 4, 1. I think I forgot to mention that, but if you take a triple of varieties, it's always in exactly 1 block. So as a pure mathematician, I'm just interested in these objects in their own right. I never think about the statistical applications when I work with them, but it's where they come from. Okay, so some properties of these designs. First, you can show, it's a little exercise to show that every T design is also a T-take-1 design with same V, same B, same K, but larger lambda. So the lambda changes, everything else stays the same. So for instance, every 3 design is also a 2 design. So that's why here in this example, the cube, it's a 3 design, but also a 2 design. Another interesting parameter is R, which is the number of blocks containing a point. It's R, the letter R comes from the word replication, sometimes called the replication number. So it's the number of farms where your variety is planted. And this number R is the same for each variety. Now B and R can be recovered from the other parameters. So that's why we just write T, VK, lambda. We don't need the B and the R to be in the list of parameters because you can just deduce them from the other ones. You just do a little bit of counting. For instance, if you look at this equality identity here, if you count the number of incident point block pairs, then you get that. So because you can either first count the points, and there's V of them, and then you count the blocks that are contain these points, and there's R of them, or you count the number of blocks, which is B, and how many times the number of points on this block, which is K. So you get this identity here. And a point block pair like this, I'm going to use this this again. It's called a flag. So a flag is when you have a point and a block where the point belongs to the block. Now, if you do a similar counting, but a little bit more complicated, where instead you take T distinct points and an incident block, then you will get this other identity. And from these two identities, you can find what B and R are in terms of the other parameters. So for instance, for T equals 2, we get this formula for R and this formula for B. So in particular, that means that, so these are integers. So this gives us divisibility conditions. So K minus 1 needs to divide V take 1 times lambda. So we get some divisibility conditions this way. Not all choices of parameters can give a design. These divisibility conditions gives us a list of what we call admissible parameters. So a set of parameters is admissible if this R and B are integers with these parameters. So even with admissible parameters, it's not obvious to determine if such a design exists. Or how many there are up to isomorphism for a specific set of parameters. So these are not at all unique. I want to show the Handbook of Combinatorial Designs. Here you can see it's a break. There's lots of different types of design. So this balanced incomplete block designs I'm talking about is not the whole book, but it's a significant part of the book. And it has tables, like you can see on the right-hand side. The list goes up to R equals 41, and there is 1196 admissible sets of parameters. I'm going to try zooming in a little bit. So you can see sometimes it's not known. So like here is an example, question mark means, or at least at the time of printing the book, it was not known if there exists a design with these parameters. Sometimes it is known that there is none, like when there's a 0 here, or it is known there is at least a certain non-isomorphic number of examples, like this one has at least this humongous number of non-isomorphic designs. And sometimes it's known exactly how many there are. So here we have 13 of those, and here this incredibly accurate and big number for this one. So there is pages and pages of results like that for all admissible parameters with R up to 41. Okay, so as I said at the beginning, I'm interested in symmetry. So what is a symmetry or automorphism for a design? So we have a point, remember we have a point set, we have a block set. Well, then a symmetry, an automorphism, is a permutation of the point set that leaves invariant the block set. For instance, here I have two of my final planes, the example that I gave earlier, and I'm thinking of it as a before and after. So that's before, and then it transforms into that. And here in this case is just a rotation, a third of a turn. And you can see, for instance, if I do this rotation, this line 153 becomes this line 153. So I kept the colors so you can see where the blocks are sent. So, but there are examples of symmetries that I cannot say it's a rotation. It's not something that comes from a Euclidean symmetry. For instance, this one here. So this means I mapped vertex variety point 1 up onto here, the middle point, etc. So I permuted all my points, and again, the colors show how the blocks are permuted. So you see the circle is now becomes one of these lines here. So at the bottom, it's what's called a cycle decomposition for the permutation. If you haven't seen this before, then don't worry about it. It's just a way to represent the permutation. Okay, so that's what a symmetry of a design is. So we like to study designs or any kind of structure that have a certain amount of symmetry. Of course, as I said before, automorphisms, they form a group, which we denote by aut D, automorphisms of the design D. So we usually want the permutation group or the automorphism group to be transitive on some type of objects. Say in this case, it would be transitive on the points or transitive on the blocks or both. And what does that mean? We say that group is transitive on X if for any two elements in X there is a permutation in G mapping the first one to the second one. So for instance, point transitive for a design would mean any point can be mapped onto any other point. So here, say I have the blue point and the red point. There is a symmetry, an automorphism that maps the blue point to the red point, and the same for if I took any pair of points. So in other words, all the points are the same. Block transitive is the same but with blocks. So any block can be mapped onto any other block. For instance, the blue block can be mapped onto the red block here, and I can do this for any two blocks. So all blocks are the same. We like block transitive designs because there's a big advantage. Instead of having to give a big matrix of data to define the design, all you need is one block and generators for the automorphism group, and then that's it. You've described your design. So you need a lot less information to describe the design if it's block transitive. So that's why block transitive is interesting. Flag-transitive is so recall a flag is an incidence point block pair. So flag-transitive means any flag can be mapped onto any other flag. So for instance, this blue flag consisting of this point here and this line here, and the red flag consisting of this point here and this line here, I can map the first flag to the second flag. That means I can map this line to this line, or this block to this block, and at the same time, this point has to go on to this point. So this is stronger than being block transitive. So all the flags are the same for flag-transitive design. And another way of saying this is all the blocks are the same. And if I fix a block, then all points on that block must be also the same. So it needs to be block transitive. And if I fix a block, it needs to be transitive on the points of that block. So that's equivalent to being flag transitive. Obviously, from the definition, flag transitive implies block transitive, and also flag transitive implies point transitive. For a T design with T at least 2, which is the designs I talked about here, it's actually a bit stronger. Flag transitive implies block transitive, but also block transitive alone implies a point transitive, and that's non-trivial. It's not just by the definition. In this project, I wanted to talk a little bit about today. We were interested in what's called imprimitive groups. So what's that? If we have a transitive group, we say it's imprimitive on that set X, so it can be points or blocks, if G preserves a partition, and we want this partition to be non-trivial. And what I mean by non-trivial is I want the parts in my partition to be not of size 1, not just singletons, and I want more than one part in my partition. If C was equal to 1 or D was equal to 1, I would call this like a trivial partition. So we want a non-trivial partition, sigma, and that's so I can think of it as coloring all my objects or points or blocks in such a way that if I take any permutation in the group, if I have 2 elements of the same color and I apply the map, they stay of the same color. So if I take 2 blue points, they have to stay the same color. They can maybe go to the green points, but they both have to stay the same color. So that's what we mean by it preserves the group preserves the partition. So for instance, the example that I gave with the cube is block imprimitive. So each, I can pair up the blocks 2 by 2, which with this picture illustrates that. And if I take, so these are like disjoint blocks, and if I move the block, one block, the other also goes to the disjoint one, so they stay in the same partition. So here my columns represent the partition. So I have 7 parts of size 2 here in this example. It's not that easy to give an example which is point imprimitive for a design. So I'm not giving one for now. If it's not imprimitive, then it's what's called primitive. The only invariant partitions are trivial. For instance, the group of the final plane is flag transitive and it is primitive. And there's lots of tools to work with primitive groups, and a lot is known about things that have a primitive automorphism group. But in this project, we were interested in looking at imprimitive. So the other case, the one where you do have a partition. And I want to have nice symmetries. So I'm looking at flag transitive and point imprimitive. That's what I'm interested in here. So first comment is that if T is at least 3, then it can't be imprimitive. So we only have to worry about T equals 2. So 2 designs. it was proved a long time ago by Higman and McLaughlin that if you have a 2VK1 design, that's also called a linear space, then it must be point primitive. So it can't be point imprimitive. So we need to consider lambda at least 2. So with a PhD student, Hongshui Liang, we looked at that question of 2VK2 designs that are flag-transitive, and we found that there were exactly 2 that were point imprimitive, and both of them have the same set of parameters. These are the parameters here. And then we proved also some things for if the group is point primitive, what does the group look like? Okay, so that's for lambda equals 2. So I'm going to skip this because I don't have that much time. So what does a block look like for flag-transitive point imprimitive to design? Well, a block would look like something like this picture. I'm transitive on blocks, and among a block, I'm transitive on the points in that block. So we have this constant, which I call L, such that each block intersect each part in L or 0 points. So it looks like this. This is an example where the L would be equal to 2. So obviously L divides K. And if you think a little bit about it, it's also easy to see that you cannot have L equals 1. So doing a bit of combinatorics, that means counting things. I can count inner pairs and outer pairs. So what I call an inner pair, a pair of points in a block that is in the same part of the partition. So like the blue pair here is an inner pair, or an outer pair would be this orange pair. So with this example here, the block B would have 3 inner pairs and 12 outer pairs. You can do a similar counting with just the parameters L, K, etc. And then you find that here, this is the number of inner pairs. It's K, L take 1/2, and the number of outer pairs is K take L over 2. Now, if you do a little bit of counting, I'm going a bit quicker here because I'm running out of time, but it's just you count in 2 ways, kind of thing. So the same as when I said VR equals BK, the same type of counting, just a little bit more complicated. We can find that we have this identity and this identity, and so it means that a flag-transitive point imprimitive to design must satisfy this identity here. Now it's easy to see from that K must be at least 6, and it must be composite. We also have an inequality on V compared to K. That one is not as obvious, and this was first in a paper by Cameron Prager in 1993, this identity also. Okay, so K equals 6 is the smallest possible block size, and this was studied by Zhang and Zhou in 2016. They classified all the block size 6 such designs, so flag-transitive, point imprimitive 2 designs. First, if you plug in K equals 6 in here, then the L must be 2 or 3, and then it's just very elementary to get that V equals 16, and then they just use computers to narrow it down to just exactly 14 designs. There are infinite families, though. For instance, here, if you take a projective space and then some specific types of blocks, you can, but not the full automorphism group. So here, this group here is a subgroup of the automorphism group, and it is flag-transitive and point imprimitive. But the full automorphism group for this example would be primitive. So for these designs, lambda grows exponentially with n. But for a fixed lambda, it was proved in the 80s by U. Davies that K and V must be bounded by functions of lambda. But he didn't say which function. So for a fixed lambda, there's only finitely many possible designs with these properties. And what we did, it was part of our discovery project. We proved that there are cubic bounds, so that K is less than or equal to this number here, 2 lambda squared times lambda take 1, and V, so this is just the K take 2 squared that I mentioned earlier. So the real result is this part here. Note this is not tight, so it might still be possible to improve this. Then we looked at small lambdas. So lambda 2 was already done, so 3 and 4. And from there, we can obtain a list of numerically feasible parameter sets, so that satisfies all the conditions such that the identity I showed just before. And then using both theoretical arguments and in a computer, we were able to classify all the examples with less than 100 points. So there is still 7 parameter sets where we don't know if they exist or not for lambda equals 3 and 11 for lambda equals 4. And I'll just finish with showing what we found. So for V less than 100 and lambda 2, 3, or 4, we found these designs here that are in this table. There are 11 designs. In this table, it looks like it's 13, but it's because 2 of them appear several times. So these two here are also among these 4 there. So there's 2 different partitions with different C and D here. For some of them, the full automorphism group is point imprimitive, and then for some of them, it's not. So I'm going to finish shortly. Here I wrote new. When we wrote the paper, we thought it was new, and then since then we found out it was mentioned very briefly in one other paper. We had asked experts, and nobody had seen this before, but so it's not completely new, but we still proved some nice things. It's a very nice example, but I'm going to stop here because of time. Thank you.
Thank you, Alice. That was a great talk. I'm happy to open up to questions. If anyone has any questions, please unmute yourself.
I've got a fairly boring question.
Yep.
It's about the word flag. This isn't my area at all, but I've seen that before in, I think they call it simplicial geometry, where it's typically got more levels. You know, you've got a point residing within a facet, which resides within a higher dimensional facet, and so on. So is that, as far as you know, is that the origin of the term flag in mathematics?
Yes. Yeah. It's the same thing. And what the reason it's called a flag is because if you think like you have a point and then like a one-dimensional simplex and then a two-dimensional simplex, like it looks like a flag.
Sure.
That's
Yeah,
why
it's
that's why it's called a flag. But yeah, it's the same thing. The
okay.
same
And I suppose there are probably a lot of deep connections between what you're doing and simplicial geometry.
I also work with designs which are simplicial complexes, but sorry, did I say, what did I say? Buildings, TIS buildings, but designs, yeah, I'm sure there's connections, but this is, yeah.
Okay, thanks.
More discrete, but I haven't thought about this.
Okay, thanks.
Do we have any more questions for Alice? I had one from a computational standpoint. Like, given any parameter set like TK, B, V, R, like, is there an algorithm that for those parameters that are sufficiently small, like does it guarantee a solution?
No, it does not guarantee a solution. For the small parameters, it's known. Let me see, like I'm looking at the book. The first one where it's 0, where I have a 0 is with v equals 15 and k equals 5 and lambda equals 2. And there's a few zeros. So v equals 15 looks like it would be the smaller one, although they're classified by R, so R equals 7. So for the small ones, the smallest ones, then they're known and they're even unique, a lot of them. But so even at v equals 15, you get one where there's admissible parameters, but no design.
Let's see. And like, as those parameters get large, like how does the computation time scale with those parameters? Is it?
Yeah, so I don't really work a lot with the computation side. Right. When you don't have also a group. Like, I do lots of computations, but I always assume that I have a group that has some properties, and that makes things much easier because I can like try groups and like try blocks, and I have a group. I just take the images of all the block under the group, and that gives me an example, and then I check if it's a design or not. So it's quite different if you don't assume anything, and if you just want the conditions to be a design. I'm not quite sure how they do the computations, but it would have to be like brute force checking a lot of things. Like yeah.
Okay.
So some of these designs have a group, trivial automorphism group. That means only the identity is an automorphism of the design. So no symmetry. There are examples where it's no symmetry at all. And I'm interested in the ones where you have lots of symmetry.
Yeah. Any other questions for Alice? No?
Thanks for having me.
Yeah, thanks very much, Alice, for a really interesting talk.
No worries.
We'd clap if we could, but I guess we're all... all right, thanks very much, Alice. Thanks, everybody.
Thank you. Bye.